really, really small, really, really fast. And then we need to start taking into account things like special relativity and general relativity and quantum mechanics. So huge portions of our universe don't work the way Newton expected them to. That's where guys like Einstein showed up and developed his general and special theory of relativity. General relativity is for things that get really, really big. Special relativity is for things that are moving very, very quickly. So general relativity is planets. Special relativity is light. And then you've got quantum mechanics, which deals with the very, very small. Weird things happen when things get real big, real small, real fast. But otherwise, Newton did great. And his laws established a lot of what we understand. So let's talk about forces. What's a force? No, it's don't. It's yes. That it penetrates us, it binds us, it holds the universe together. No, that's Star Wars, not the force. What is a force, Luis?
Force is something that makes movement.
Something that makes movement, possibly. It can make movement. Does it always make movement?
And produce energy. No, energy no. That's work.
That is work. It's true. Does a force always produce movement?
No.
Are you moving right now?
No.
Do you have forces acting on you?
The gravity, like I'm putting force in this chair, the chair is pulling me back.
So the chair is holding you up and gravity is pulling you down. So there are forces acting on you, but you're not moving.
Yeah, because of my inertia.
The inertia is connected to that, but it's not the same. Manuel. It is. It will be. How do you know? You read the textbook already. You are ultimately correct. We're not there yet. But you know what? We can write it down. A force. A force is going to be given to us by this, F equals ma. That's one example of a force. This goes back to what Luis said. A force is something that produces motion. So I've got a mass, I've got an acceleration here. If you have if you are accelerating, there must be a force acting on you. But that's not exclusively true. It's not always true. Because Manuel, you would say that you're not accelerating right now as you sit there. Probably. I'm willing to bet. But are there forces acting on you? Yeah, like Luis already said. So what's a force?
What are the types of forces?
We're going to get there. What's a force?
Like plain old definition.
How do you know that a force is present?
Feel it.
Okay, you feel it. Feel it acting how?
When you jump like that.
So when you jump, you come back down. So there's a pull downwards. Okay, that's what's...
An object reacts.
You're trying to find the most convoluted expression for this thing, and that's okay, but that's not necessary. Let's simplify it for you here a little bit. A force. Any push or pull. Really simple. If something pulls you, or it pushes you, or holds you up, there's a force acting there. This is going to come later. This F equals ma business is going to come later. We have units for force. This actually gives us an interesting set of units for force. M stands here for mass. Does anyone know what mass is measured in? Kilograms. The A stands for acceleration. Acceleration is measured in what units? It's not a dash, it's a slash. It's meters per second squared. So if a force is equal to a mass times acceleration, as Manuel already said, then, sorry?
Global unit is called newtons.
Well, we'll get there. Look at what we've got here. A force is a mass times acceleration. A mass is measured in kilograms. And acceleration is measured in meters per second squared. So units of force, or one of the sets of units of force, is actually called a kilogram meter per second squared. That's a little weird. We don't like to measure, well, I mean, we do. It's just not always convenient to measure forces as kilogram meter per second squared. Because what do you do with an object that's not accelerating? it makes less sense for us to talk about a meter per second squared. So as Luis already said, the other unit that we use as units for force is the Newton, after Sir Isaac. Okay? So 1 Newton is equal to 1 kilogram meter per second squared. And there we go. We got newtons. A new unit for you. There are 4 fundamental forces that make up all of the forces in the universe. And then there's going to be a whole bunch of other ones that we talk about, but they're not considered fundamental forces. The fundamental forces are known. That's not the normal force. Gravity is one.
Magnetic force.
Neither of those are fundamental. They are forces, but they are not considered fundamental forces. That is one. Gravity is one. You know the names in Portuguese? Those are all forces that we're going to talk about. We're going to talk about the friction force
What about our own force?
and applied force.
Yeah.
We'll talk about those too, but those aren't universally fundamental. Tristan? Kind of. We call it electromagnetic, but yeah. I didn't hear it. Electromagnetic force is a fundamental force. And then there are 2 that I'm willing to bet you've never heard of, and that's okay. One of them is called the strong nuclear and weak nuclear.
What is that?
Those ones I didn't study, but I heard about it because it's complex.
So the weak nuclear force is the force that holds protons and neutrons together in an atom. And the strong nuclear force is the force that holds quarks together to make the particles protons and neutrons and all those kinds of things. So these are the fundamental forces, and then everything else is basically just a derivation of these forces.
Okay, so basically that's what holds us together.
These are the ones that hold you together. Actually, all 3 of these hold you together, yeah. The strong nuclear force is the strongest of the 3. 4 of the 4.
If you were to pull apart a quark, would it be like a boom?
You can't pull apart a quark. Quarks are fundamental particles.
No, man. You know that we can definitely pop.
We don't know for sure. But as it stands today,
What's the thing right before quark? Like a little bit.
protons, neutrons, electrons, they're all made of quarks.
If you pull those apart, then like, do they make a big basically?
If you could, yes. The way we pull them apart right now is we don't pull them apart. The only way to break this is by having them move very, 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 very quickly and then smashing them into each other at a fraction of the speed of light. Hence, this is what the Large Hadron Collider, buried underneath Switzerland, this is what this is designed to do. Break the strong nuclear force by smashing these things together at almost the speed of light.
So that would like give us a lot of energy at once.
It takes a lot of energy to do it, and there's a lot of energy produced, yes. So let's start a little bit more simply, and let's talk about gravity. What is the force of gravity?
Minus 9.8.
No. What is the force of gravity? Define it with words.
Pulls you to the center of the earth.
Hands up.
Oh.
Luis.
It's a force that pulls you to the center of the earth, always down. Not down, like the center of the earth in general. And it could be stronger or weak, depends on your height.
Altitude, you mean?
Yeah, altitude.
Yeah. That is a very specific case for gravity. On Earth, that's true. But as soon as we leave Earth, now, what about other sources of gravity?
These stars can be a source of gravity, but like gravity is such a complex thing because it can change the time, like the way time works.
Connor.
Gravity is just it's a force that expands the universe.
Actually, it doesn't expand the universe.
Really?
Gravity doesn't cause expansion. If gravity caused expansion, you would be expanded.
I don't like that idea.
I don't either. Tenjo. We're getting better. I like this. Gravity, the force of gravity is a force of attraction between masses.
Oh, that's why like
So, as for, sorry?
that's why bigger things tend to have more like gravity force.
Right. So that's why on the Earth, anywhere you go on the Earth, you're always attracted to the center of the Earth. The moon, which is slightly smaller than the Earth, if you were on the moon, you would be attracted to the center of the moon, but not perhaps as strongly. So the force of gravity is a force of attraction between masses. When I say mass, masses are always measured in kilograms. And does anyone know what mass is, like the definition for mass?
No wait. Oh.
It is not weight.
Yeah.
Weight is different. Tenjo. Sorry? What do you mean? Kind of. You're almost there. But size, overall size, doesn't necessarily mean that things are more massive. I could have something really big and something really small, and the small thing is more massive than the big, because density is a part of it too. Absolutely. Manuel. That's not what mass is. That's what mass does. James. Smart. I like it, but no. Mass is the total amount of matter in an object. So we typically think that the larger the object, the more mass it has. That's not always true, because density plays a huge part in this. You can have objects like things like that are made of lead that aren't very big but are very, very massive because the particles are very, very close together, and there's a lot of them packed in there.
The center of the Earth, for example, is really dense, so
It's fairly dense, yeah.
yeah, so that's why it's the thing.
I mean, the Earth itself is all of the Earth is pretty massive, which is why gravity's a thing.
Oh, okay.
So if mass is the total amount of matter in an object, what's weight? Mass is the amount of matter in an object. What is weight?
Oh,
The gravity impact on the mass, like the way that gravity like applies force in the mass.
Yes. Yes. That is weight. Okay? So weight is defined as the gravitational force on a mass.
wait, so you're saying like when I jump on the scale, the gravitational force is relevant to my weight on Earth versus
Right.
my weight, for example, on the moon.
Right. So in those two places, because gravity is not the same in those two places, your weight is not going to be the same, but your mass hasn't changed. Because mass is the amount of matter that makes you up. So the only way that I could change your mass between the Earth and the moon would be to cut off a limb. Yeah, sure. Or I could make you work out, that works too. But you'd have to decrease the amount of particles that make you up, or increase the amount of particles that make you up, to change your mass. Weight is gravitational force acting on a mass.
Okay, I still don't understand though, because with your actual mass, like with kg, that's literally a weight that we would use, that we can.
Careful with how you use the language. We call them weights, but they aren't weights, they're masses. This is where, again, just like in the first chapter, just like in the second chapter, you're using vocabulary that you assume means what you think it means based on the abuse of the English language that we've given it. Like you go to the gym and I'm going to put weights on. No, you're not putting weights on, you're putting masses on. The only reason those masses have weight is because of how gravity is interacting with them. Weight are actually just masses. Weight is how weights aren't a thing. Weight is a concept of how strong gravity interacts with the mass of a given object.
Okay, so what do I actually theoretically weigh? Yeah, so then what do you actually weigh? Exactly.
Depends on where you are.
No, but I know what I weigh here.
Okay. So what do you weigh here?
Okay, if I weighed in space, like if I was in space, like I know it's like
Okay,
I
so
think-
let's say, so if there is no gravity,
yeah.
can you have a weight?
Weight doesn't exist. You just said that.
Can you have weight if there is no gravity present? No. But has your mass changed? No, because mass is the particles that make you up. But if I remove you from gravity, you have no weight. You are now weightless. Because weight is just a measured value of how gravity is interacting with your mass. Most people don't ever leave Earth. And so we don't really care to distinguish between masses and weights. We'll say, oh, how much do you weigh? Oh, I weigh 100 kilograms, maybe. I don't know. But that's not what I weigh. That's what my mass is.
Do I actually?
You know, your weight in space is going to be 0. Your mass is going to be 45 kilograms.
Okay, so my mass.
But your weight is going to be
okay,
0.
It is. It would be if I was in
Okay.
space. If I weighed like 40, 50 kilograms. Then
So mass is constant throughout the universe for an object. It doesn't matter where I put you in the universe, assuming I can get you there instantaneously, like you haven't had time to starve or put on a bunch of extra weight. I use that word improperly again. You haven't had time to add to yourself through the consumption of additional calories. Your mass hasn't changed. It's constant for you everywhere, but weight changes depending on where you are. And we're going to do some of those calculations here in a sec. The formula for the force of gravity is the following. F equals mg. And often, this F is given a subscript that goes along with it. We call it Fg. Fg equals mg. And this is not F times G, this is just Fg. Like Manuel is just Manuel. This is just Fg. Stands for the force of gravity.
It's usually like the gravity force, like I remember that I have done some questions that the teacher put the G like a 10, like to be easy to calculate, like a variable that.
Yeah, it's not as accurate, but yeah. So Fg is equal to mg, where m is your mass. And little g is gravitational field strength which on or near the surface of Earth we already have a value for. Gravitational field strength on or near the surface of Earth is 9.81 meters per second squared. On or near Earth's surface. And when I say near, I mean like within about 100 kilometers of the surface of Earth, yeah.
what about like dips in the earth where the surface goes below sea level?
It's less to do with that and more about the density of the ground beneath you. We're very close to it. So, gravitational field strength is often reflected as an acceleration. Like, these are units of acceleration. Because gravitational field strength causes an acceleration, and the acceleration that it causes underneath the surface of Earth is 9.81. So that's what we're calling gravitational field strength. basically it's an acceleration due to gravity. Manuel, you look very uncertain. What have I done? Okay. So, G, little g, depends on a few things. Two things, really. The size of the object creating the gravity and how close you are to it. There's just not enough space there. It looks like one word. It's to it. The size of the object creating the gravity and how close you are to it. Any object with mass creates its own gravitational field. Most objects, though, are too small for us to have for them to have a measurable effect. For example, all of you have your own little gravitational field that acts on everything else you're kind of near.
So I have just a very small, just little
Yep. And we're actually going to be able to calculate it, your own gravitational field strength. We're going to in a couple days. But you're so massless that the amount of gravity you create is minuscule compared to everything. No, you wouldn't even attract dust. Yeah. No. No, like honestly, no. The amount of gravity you create is so small, it doesn't act on anything. So you need incredibly large objects. We're talking planets, moons, even our moon. I'll give you some values here. So on Earth at sea level, little g, we've already figured this out. You did a lab to identify this, is 9.8 meters per second squared. The moon, as large as our moon is, and the moon is pretty big. If you've never taken, well, I mean, I guess it depends on if you did astronomy in Science 10, depending on who your Science 10 teacher is. None of you had me. The moon is actually almost the same size as Mars. That's how big our moon is. About the same size of our moon. The strength of gravity on the moon is 1.6 meters per second squared. So it's like 20% of Earth's gravity. Much, much, much lower than ours. Jupiter, on the other hand, has a value for G of 24.5. Meters per second squared. So gravity on Jupiter is like 2.25 times Earth's gravity. But Jupiter is way more than 2.5 times bigger. So there's... Sorry? The sun is actually our next value. The acceleration due to gravity on the surface of the sun, assuming you could stand there without incinerating, is 274 meters per second squared.
Whoa. So that would just like pancake you right there.
You betcha.
Yeah.
Black holes have much more.
Yeah.
Technically, it's infinite. Technically, it's infinite. Oh, sorry. I didn't round this properly. It's 275.
Dang it.
I didn't round it properly.
So you mean like if we just be like broken down to our like tiny little particles?
Okay, so we're going to yes. No.
No, like if we're in a black hole.
Can you wait just a little bit? Okay.
Would we be broken
So,
down to our particles?
we're going to determine your guys' weight a few different places. Your weight on Earth, the moon, and Jupiter, and why not? Let's also do what you would weigh on the sun. Let's add that down there at the bottom. Okay, so how many of you know what your mass is? Jasmine, do you want to volunteer? Actually, you know what? No, I'll volunteer my own. I want you to write your own, though, on this line. Whatever your guys' mass is, assuming you know. If you don't, take a look at your driver's license, and we'll just go with that.
Oh no, my driver's license is inaccurate. They asked me, they didn't even weigh me. Did they weigh me?
No, they don't weigh you. They ask you for a ballpark.
Sorry?
They ask you for a ballpark.
Yeah, they didn't actually weigh me.
Okay, I want you to put your own mass in there, whatever your mass is. My mass is give or take 100 kilos.
I'm too, like,
Depending on the time of year, I definitely put on some father weight. So I might be a little bit more than 100 kilos. Put your own mass in there.
my mess is always relative. I have to see all executive mass here.
Let's see how accurate.
Well, you don't run through it.
Okay, so 52.2. So if you're unsure, if you know what your mass is as far as pounds goes, you take pounds and your mass in pounds and divide by 2.2. So this tells you that I'm about 220 pounds,
This thing's off by
more or less. Okay, so if you know your mass in pounds, take that number and divide it by 2.2. That will give you your mass in kilograms. And we've got to use kilograms. Kilograms are the scientific standard unit for mass. It's convenient. Yeah, it's not nice for my overall level of fitness, but it's mathematically convenient, yes. My mass is mathematically convenient.
Yeah, like, in other countries of America, use kilograms and liters.
Yeah,
I don't think
yeah. Have you written yours down?
Yeah.
Okay, cool. Let's keep going. So, your weight on Earth is going to be whatever your mass is times g. So my weight is going to be my 100 kilos times 9.8, giving me a mass of 980 newtons. So, punch that in there. Write down what your weight on Earth would be. Now let's do the same thing for the moon. Fg equals mg.
Hold up, nobody ready.
And my mass hasn't changed. My mass is still 100 kilos. But the gravitational field strength on the moon has changed. It's now 1.6. So where I was 980 newtons, now I'm only going to be 160 newtons. On Jupiter, well, that's going to be Fg equals, I don't have a lot of space, so I'm not going to write the formula down again. My mass is 100. The Jupiter's, acceleration due to gravity is 24.5. So it's going to be 2,450 newtons.
And how many newtons does it take to break this flow again? I wrote it down, but I totally forgot. This is how we learn, man. This is how we do.
2,300. So if I stepped on your head on Jupiter, I could crush your skull. Is what that means. Is what that means. Assuming that I was strong enough to lift my own leg on Jupiter, yes, I could put my foot down on your head and crush it. Okay. Okay. And the weight on the sun, this gets ridiculous. 100 times 275 is going to give me a mass, or give me a weight rather, of 27,500 newtons.
How far underwater do you have to be to get that amount of pressure?
Okay, so just to put some perspective, yes, yep. Just to put some perspective here, the upper leg muscle, your quad, one of the biggest muscles in your body, if not the biggest, typically, on average, exerts a force of 1,250 newtons. So my weight on my quads, assuming I'm an average human, could not hold up. Actually, they could just. Between the two of them, no, they couldn't. They'd be just short. I couldn't stand on Jupiter because my quads aren't strong enough to hold me up,
No,
assuming I am an average human.
No, but like, that's not the only thing that helps you stabilize. You have your.
Those are just the muscles to stand, to get up off the ground. Okay. Okay. Okay.
Like, it's physically possible to get up and
Based on my mass, assuming I'm an average human, the average quad strength for a human being, according to the medical journal I just Googled, is 1,250 newtons. So 2 quads is going to be 2,300 newtons. My weight on Jupiter, though, is 2,450. So my weight just exceeds the average human quad strength on Jupiter. But if you have also average quad strength, your weight will be less than mine because your mass is less than mine. So you could stand theoretically on Jupiter where I cannot. I am very near the border between like being able to stand on Jupiter and not. I couldn't get my own mass off the ground. Khalil. Average. Oh, that's going to be wildly different country to country.
Can you stand on Jupiter?
Average muscle strength is more universal than average weight.
Can you actually stand on Jupiter? Like, is there something to stand on?
There is a solid surface somewhere, yes. There has to be.
We don't know.
It's technically a gas giant, but at some point the density would be so great that the gas would solidify. I don't know where that is, though. Jupiter has to have a solid core. Don't know. That's beyond the scope of what I'm trying to teach you now. Flip the page.
It's interesting though.
It is super interesting. Flip the page. Here's what we're going to do. With the time that we have left, and we have 15 minutes left, here's what we're going to do. We're going to try and figure out how high you could jump on the surface of the moon and the sun based on how high you can jump on Earth. So here's what we're going to do. You guys are going to get into groups of 3. You are going to measure your best vertical on Earth. Okay? And so this is going to be a straight leg vertical. Straight leg. Okay? So no, you're going to crouch. Okay? You're going to crouch, you're going to squat, and you're going to extend. It's not to see how high up, like you're not going to like jackrabbit your legs back up into yourself, right? It's just whatever that is. Your feet off the ground. Okay? Straight leg. That's what you're going to try and do. We're going to measure that vertical. Using that vertical measurement, we're going to figure out what your initial velocity must have been. Okay? So, the vertical is going to be what value? It's going to be in meters. So that's a displacement. I'm helping you here because the test wasn't super great. So we've got a displacement. At the top of your vertical, what's your final velocity? We're looking to find your initial velocity. And what other piece of information do we know because you're jumping on Earth? The acceleration is negative 9.8 meters per second squared. So all you've got to do is measure d to find VI. So that's what we're going to do now. Once you've got your VI, we're going to assume that your initial jump velocity is going to be the same on the moon and on the sun, which isn't totally accurate, but we're going to assume for a sec that it is. And using these two values, this would actually be negative 275. you're going to go work backwards to find your max height off the surface of the moon and the surface of the sun. So this is a relatively straightforward thing. Find a group of 3, grab a meter stick, and find your vertical. Go.
What if we jump higher than us? I know somebody who jumped 99.
I'd like to see you jump over a meter straight line.
I can only.
Yeah, straight leg, I don't believe
I can hit 80.
Straight leg?
Bent leg, I can get up.
Bent leg is entirely different.
Bent leg, I can
Okay,
go on.
figure it out. Yeah, you can go into the hallway, you can do straight, don't hurt yourself.
I don't trust you with the stick, bro. Give it to Zay.
What? And you want to make sure that the stick is straight up and down. Something against the wall might not be bad. From when? How long does it take you to get home?
Wait, are we going? We can go up.
Open the button.
We can stay right here.
Alright, fine, stay right here.
Take it out of here.
Where are we
See you
going?
tomorrow.
I don't know from not yet.
Bring your phone, we'll probably need this.
Figure out your vertical, guys, and then come back.
I don't think that I have room.
Except for Khalil. Khalil, you go.
Okay, I don't think that I have room, brother.
Well, go join someone. You can leave your stuff. All you need is a single writing utensil.
Okay. Was the distance that we jumped was the same? So what is the distance? No.
He has it. It's on his phone.
Oh.
Hey, tell us measurements. What do we do?
Yeah, that's why I'm compare.
Get me a piece of that ass. Bro, class is almost over. It's like 4 hours. I'm not. Alright. Who?
I just got on the sea.
I think that the ruler was upside down.
No shit.
Yeah, it's upside down, like.
Okay, we can just do this different.
Just do it.
Like what?
Dude, this is 1 meter minus that.
Yeah.
Bro, however high I jump, this is 30 minus however high I jump.
Maybe about how many degrees? 39. So it's 39 minus 27.
39 minus. That's 12 meters.
Yeah, 12 inches.
Oh, jump right now? I think I can jump higher than a foot. Well, I can definitely jump higher. I'm pretty much like a foot jump. Okay, jump. Bro, you don't really bang. I can easily jump higher. Try. Once you've got your heights. If you put your timer wrong, my tweet is. I think it's on the
I think you're thinking like if you can jump higher than a foot. Yeah, probably not.
Well, some people can. Mike got almost 58 centimeters. Manuel, Mike, and Connor got pretty good ones. But they're also, you know, fairly athletic. Meter 6. I'll take the meter 6 back up here at the front.
Okay, so we're gonna finish this tomorrow?
Sorry?
We're gonna finish this tomorrow or we can do it at home? Like
Your homework is to figure out your max heights
okay.
and the time you'll be in the air. Yes, this I want you to finish tonight. You've got the only piece of information you need. I want you to finish it tonight. VF squared equals VI squared plus 2E.
Connor is an absolute monster.
Wait, Manuel, what did you say for me?
I don't.
58.
58.
Remember, that's centimeters. Guys, remember your heights need to be in meters. But you almost certainly measured them in centimeters. So convert from centimeters to meters. Divide by 100. It's an easy fix. Okay, and then once you've got your displacement, it's easy to work your way backwards. D gives you VI using VF squared equals VI squared plus 2AD. Find your V0, and we're going to assume that that's the same on both of these surfaces, the moon and the sun. This I want you to finish for homework. I want you to come to class tomorrow, being able to tell us what your max heights are and how long you'll be in the air on both those places. Bell's going to go here in a sec. If I've got my meter 6 back, you guys can pack up. When the bell goes, you may also go, welcome to Forces. We'll see you tomorrow.
Improve my vertical. Bro, I'm not. Bro, I thought I did my vertical.
Yep.
I can do it. James?
Bell hasn't gone, James. Hasn't gone yet. 224.
Like 40 meter run.
I don't know.
I don't run. I was in endurance.
Bro, I can barely go 100 meters without dying.
I sprint. Okay.
I saw that, yes.
Are you good? Did we do good?
I haven't looked at it yet. Have a good day, guys. See you tomorrow.
Easier now?
No.
No.
Leadership students are going to evaluate it tomorrow.
Manuel, I sprinted 26 for 50 meters, and then 100 meters is a 101.
was a joke. We just recorded it. We laughed. We didn't prepare at all. They did. And I was there. I was
So what's
recording.
your grade